So here's a pencast about IPs or intellectual property for FPGAs. Don't mind the date, I know it's a bit outdated, but it's been updated quite a few times since 2012 when it was initially made. So what we are looking at today is get an understanding of what an IP core is about, get an overview of the different IP types, look at a couple of examples, discuss why simulation still is important, and discuss how we can verify an IP block, and then try to summarize a bit. And then there's a lab for you as well. On Blackboard, chapter 13 from this book, Rapid System Prototyping with FPGAs, is available as PDF, and you should probably run through it to get an overview of the text that supports these slides. So what's an IP? Well, IP is an abbreviation of intellectual property. IP or intellectual property is relatively broad and basically it just refers to creations of the mind. So that could be anything, an invention of technical character. It could be some literature or an artist's artwork or symbols or names or images, photos or whatever designs that is used in some kind of commerce. So it's a very broad term, but we'll use it a bit more narrow and focused on the usage in an FPGA. An FPGA IP can be defined as a reusable design block. There are different types of IP, hard IP, firm IP, or soft IP, as we'll discuss in the following slides. But an IP is basically just a functional block with some fixed and defined and tested functionality, and it typically refers to a pre-verified functional design that could be, well, that one design group could obtain from another design group outside the local design team. So if you split into half in the class and one group works on an IP block that can sample data and another group works on an IP that can process and filter data, and both are wishbone compatible, for instance, you can swap IP blocks and integrate them if they are compatible to whatever standards you have met. So in broad terms, it's just encapsulated functionality that you basically can share or obtain from someone else. The typical design flow when we want to use an IP, well, I won't read them out loud, but here they have stated 22 bullets or 22 points that could make sense to do the work in that order, and it looks a bit like what we see when we work in projects and we have to work with a delimited task, but pause the video for a minute or two and read through them yourself, and then you can discuss them afterwards. Your own IP block or choose a pre-built IP block and want to integrate it into a system, we should bear in mind this figure for co-design. Co-design is basically when we have a given functionality that we want to split between hardware and software. The co-design figure here shows the overall steps. They are somewhat similar to what you saw on the previous slide, where we always start out with having a system description. That would be the functional description of what we are trying to build. Once we have it specified and divided into functional blocks, we would typically do some hardware-software partitioning to figure out what functionality needs to be implemented as hardware and what goes into software. This partitioning results in some blocks that are intended for software, some that are intended for hardware, and specifying and clarifying the interface between them. Following that, we would typically have some activities we could call system integration, where we test both the hardware and software blocks together. But basically, co-design is about this iterative process here we could have, where we partition our design into required functionality in terms of hardware and software, implement it, integrate it and test it, figure out that we might need some refinement or optimization, then we can do some repartitioning, refine it a bit, and optimize whatever we have designed here until it fits our needs. And if we can do that in parallel, so one may be occupied writing software where another one might be occupied implementing hardware, it could be in terms of an IP or building hardware on a PCB or whatever we are doing, that makes sense, and that is more or less the basics for co-design, doing things in parallel. When we look at IP blocks, we can distinguish them into 3 overall categories, where one is soft-core IPs, the other one is firm-core IPs, and the last one is hardcore IPs. Soft-core IPs are implemented purely in HDL, that would be VHDL or Verilog, with either no or minimum optimization for a specific target technology. Target technology could be if it is a Xilinx device, if it's a Spartan or Vertex or whatever device, or if it's one of the other FPGA vendors. If we have that in mind, we can optimize specifically for whatever resources may be in the selected target technology, but typically softcore is not optimized for any of these. It is just pure VHDL, so it's very portable. The firm core is also generally implemented in an HDL, a hardware description language, as VHDL or Verilog, and it has, in contrast to this pure soft core, been optimized for a specific target technology. So that means it might utilize some of the specific target technologies, such as, for instance, block RAMs, DCMs, PLLs, or memory devices that may be on board that device. That also means the implementation, optimization that the tools perform, they are aware of the physical layout and physical whatever we have in our target device. And that can allow a more efficient implementation, and it can give us an improved performance, either in terms of what capabilities the core has in terms of processing power, or how much power it uses or consumes, or the area that it takes up on silicon. The last category is the hard IPs, where we have some fixed logic functionality in the device. In the Spartan 6, for instance, we have memory controllers, and we have some SerDes, serial communication interfaces, and so on. So if we make use of them, they are locked onto that specific target device, and that's basically the definition of the hard IP. So that's how we can distinguish them very broadly. If we take a look at one of the soft core IPs that are available on opencores.org, it could be this Wishbone UART, a Wishbone compatible UART that can be implemented, for instance, in our Spartan FPGA. We can see on the web page it is Wishbone compatible signal with this WBC symbol over here. If we open up the package or the top design file, we can see that we have all the Wishbone signals required, and then we have the additional UART signals in the entity as well. All the modules that exists in this UART are written in pure VHDL. No target specific instantiations occur. So this is an example of a, I would say, relatively simple but pure soft IP implementation. A firm core IP could be, for instance, also a project on OpenCores. It could be this LCD controller intended for running an LCD panel. It does not seem to be Wishbone compatible, but still it is on opencores.org. If we take a dive into the repository where the RTL source code is available, we can see here in the trunk we have different folders available. We have some design folders, we have some implementation, and we have also one called CoreGen. And if you have worked a bit with Xilinx, you will know that CoreGen is Xilinx's core generator that can utilize some of the built-in features in the FPGA, like for instance block RAM and multipliers and so on. I would guess that a display controller would probably utilize some of the block RAM available in the device. And if it's an assumption that we need block RAM, well, it can be across multiple vendors of FPGA still. Both Xilinx and Altera and others have something similar to block RAM, but they need a target-specific implementation for that family in order to work. So this could be one example of a firm IP where we utilize some specific features in the FPGA families. Here we have opened up some of the contents in this LCD controller, and we can see over here on the left side that we have a DCM instantiation. That means we have a clock generator that generates a 100 megahertz clock. It takes a 100 megahertz clock and it generates a 6.25 megahertz LCD clock and certain other signals as well. And this presumes that we have a clock management system, in this case a DCM, or if it was in another FPGA family, it would be another clock management component that would need to be instantiated to create a stable system clock. And over here is the entity declaration where we can instantiate something around our dedicated resources inside the FPGA. The hard IP is an example of a fixed silicon functionality that would be available on our FPGA. If we look at the Spartan 6 family that we are familiar with, we can see that depending on whether we have an LX or LXT device, we have different features on board. We have some embedded hard IP that might be memory controllers and things that are suited for processing, or it could be a PowerPC core or some high performance serial I/O or different other things, memory controllers. These things are not generic across multiple FPGA families, and they are dedicated to one FPGA family or one vendor. For instance, PowerPC has been available on Xilinx devices, where Altera has offered some ARM devices on board. So that can, so to say, that can lock your abilities to work with different vendors if you have requirements for a hardcore IP to be implemented in your design. It also means the hard IP is on the silicon. You cannot unplug it and utilize whatever resources it takes up for something else. It is dedicated for that given functionality, and typically that would be something you base your selection of FPGAs upon as well. Here's an example of hard IP usage on the Spartan 6 LX9 board, where we have, in our case, we have a development board with some fixed hardware available. On the back of the board we have some memory. That means inside the FPGA we also have a memory controller that is a hard IP. Here we can use this core gen. It has something called a MIC, that would be a memory interface generator, that allows us to create a memory controller on the device and interface towards a standard DDR memory bank. And this is another case of hard IP usage that could be very typical in a setup like this. When looking at IP blocks, we could categorize IPs quite roughly into the following categories. If you look into chapter 13 in the book, you can read it yourself, but we have typically some signal processing or some memory handling or processing of images or communication channels, or our peripheral or bus interfaces like a UART or I2C or something similar. If you take a look at opencourse.org, it probably looks something like this. It did when I wrote the slides, at least. Here we have other similar categories that the IPs that are available are categorized into, and this is basically, it's not a rule, but it's just to put them into overall categories so we can see what functionality is available and what IPs we can download and work with. So when you're looking for a given functionality and for something you have to implement inside an FPGA, you have to figure out whether you should design and create it yourself, or if you should find a suited IP and buy it. We could also call that make versus buy decision, and that's rather important to figure out before you approach. So basically, you need to figure out what is my IP to do? What can the available IPs do? What design functionality do I require? What requirements have you written? And what's the functionality of the available IP blocks? Again, that comes down to that you need to craft some very thorough specifications. And again, where you can use standards for communication or standards for intercom, like we use Wishbone. That could also be AXI or PCI Express or whatever it may be. But where you can lean against the standard, there is a bigger chance that you can find something reusable and find something off the shelf that you can use to fulfill your purpose. When we talk about writing specifications and using standards, it's also about understanding the interfaces that we can act against, the functionality within the IP, that we are able to simulate available IPs to figure out if they have the required functionality for our needs, and also that we have perhaps a good test bench for verifying the functionality, and that we have some options for verifying functionality if we try the IP in our own design before we decide to either buy an available IP or download it or make one ourselves from the bottom up. Here's a number of decision factors that you could consider when you need to figure out if you should make or buy an IP. I won't read them out loud, but pause the video for a minute or two and read through them, and we can have a discussion in class about what do you find important. Typically, when we browse different IPs, there's different options. If it is commercial IPs that you should buy, there is often a try before buy option. That means you don't need to pay for it before you can try it out. You might be able to download it and get a limited license where you can synthesize and implement it for a week or so, or you can download it in a version with reduced functionality or where the functionality runs out after a certain amount of time or something like that. Even though you can download commercial IPs, of course, it might take some time to integrate it into your design and run it and write an appropriate software driver for your hardware and so on. But you should, when you evaluate an IP, also look at what tests do we have available. Do we have some measurements? Do we have some metrics for how much silicon area it takes up? Do we have available test benches that comes with the design? Is there one or more target implementation examples, for instance, where it is implemented on an evaluation board and you might get access to that evaluation board to try it out instead of having to build a lot from the bottom yourself? It could benefit your evaluation process if you can download it into an evaluation board and try it out in the real application. Again, a key point here, that IP cores can most efficiently and effectively be evaluated when they are implemented within the targeted FPGA device. That is, well, almost obvious because you can simulate and you can verify in a test bench. You can do that with a lot of functionality to figure out how it works. But to try it out in your real application, you most likely need to try it on a target and verify its performance. But still, even though we can download it and try it out on our target, before we do that, we should get a functional simulation of the IP where we have a test bench that mimics our reality and we can see what happens inside the IP and if it works as intended. And we can probably analyze a lot of the interfaces and functionality through simulation. So that is rather vital that one or more test benches are available. Just as when we work with software, we have typically when working with the FPGA IPs, we have different licensing options available. So it can be a paid IP where you just buy it and pay for a one-time settlement when you can use it all that you want, or you might have to pay for a royalty for each IP that you ship with your product. The license can be site-based and so on. There's a lot of things to consider here, and it is just like software. It might be open source, but you might have to share whatever work you implemented in, just like some of the GNU licenses. But again, if you do it commercially, when you get a a job and need to be an FPGA designer afterwards, you need to take into considerations if you use open source IP cores. What are the licensing agreements that you have to fulfill? Here is a license text in the top of one of the files in this LCD controller we looked at previously. It follows a GNU general public license, same as pretty much as any open source or a lot of open source software does, and you can find the details about the GNU license. Well, you can find the references on your own. It is probably somewhat similar to a lot of the modules available in Linux and so on. So to summarize it a bit, IPs are, well, it's just a name for encapsulating a given functionality into, in our case, an FPGA, VHDL or Verilog block. An IP can reduce your development time a lot, especially if you can find an IP that suits your needs exactly. Then you don't need to develop it from scratch. On the other hand, if you have some functionality you need to implement, you should consider encapsulating it as an IP so it has limited functionality that is specific and encapsulated, so you can test it isolated, and perhaps you can even distribute or sell your own IP afterwards if it fulfills someone else's requirements as well. That's basically it. There will be a couple of labs where we can work with our own IPs, but that's it for this pencast.